Okay, so thanks to the organizers and ICTS for hosting this GFD program. So normally I'm currently in the ocean science department. And I talk a little bit. Usually, the kind of things I talk about is more on the practical or the modeling side. So thanks to the organizer for having more theoretical flavor to this. I normally don't get to talk about the theoretical stuff. So as advertised, I'm going to talk about the Eady problem today. I'm a simple person, so I'm going to talk about simple things. So the Eady problem is fairly simple. So for those of you who don't know the Eady problem, I'll go through what the Eady problem is. For those of you who know the Eady problem, you could be thinking, well, we know everything about the Eady problem. What is there to talk about in terms of this revisited? So I'll come on to that in the second part. So first thing before I go on, I've been known to talk really fast. So if you think I'm talking too fast, please just raise your hand. I'll slow down. Okay, so there's two parts of this talk. Initially, so this is the first time I got asked to do an extended talk. So I thought, well, do I even have enough stuff to talk about? And then obviously I put too much stuff in. So now, so this is false advertisement. I'm not going to talk about everything here. So I'm going to, in the first part is going to be more introductory. So I'm going to talk about baroclinic instability related to balanced motions. And then I'm going to talk about the Eady problem as a kind of a working example. So there are normally three, so if I were to do a full talk on this, it will be three parts. So the first part would be on the mechanism leading to baroclinic instability. So this thing called the CRW mechanism, or the counter-propagating Rossby wave mechanism. So that is the thing I will be focusing on today. These other two parts which are somewhat new is to do with the instability characteristics of this Eady problem, and particularly the symmetries underlying the Eady problem. So it turns out the Eady problem is governed by what's known as a PT-symmetric operator, is a non-Hermitian operator. So this bit I will float a little bit. I won't go into very much detail about it. It works for the modified Eady problem as well. The thing I do work on quite a lot is parametrization, but for time reasons, I'm not going to talk about this at all. So I will hope the organizers will upload the slides and you can have a look at the slides and what I write to, regarding parametrization. For the purposes of the talk, I'm not talking about it. But you feel free to come ask me things about it. So the first part is just on the standard Eady problem. The second part, so this is essentially a long introduction to the second part. So the second part, we're going to look at the Eady problem in the presence of a slope. So you can think of this as baroclinic instability over things like the continental slope. And the focus on that would be on the, so in the presence of a slope, how is baroclinic instability modified? And in particular, how is the CRW mechanism modified? Okay, and there's some other implications of parametrization, but again, I'm not going to talk about it. Okay, so first part would be the overview. So baroclinic instability, so is some sort of fluctuation in, there's some sort of preferred scale for fluctuation. So in the ocean, these are called mesoscale eddies, or mesoscale dynamics. In the atmosphere, this would be the synoptic variability, as Carsten talked about yesterday. So usually these manifest as fairly energetic regions. So in the ocean, this is a diagnosis from the ocean eddy rich model. So this is a 12-degree global model, instantaneous snapshots of the surface current. So you can think of this as like the square root of the kinetic energy. So what you have is you get these loops and these kind of small scale, somewhat non-linear features coexisting with the western boundary current in this case. So the mesoscale eddies I'm talking about are these little features, little fluctuations on top of the loop. All right. In the atmosphere or in the ocean, if you do it from an observational point of view, it's a bit difficult to visualize flows. So normally you need something that's dragged around with the flow. So in the atmosphere, what you have is you've got clouds. So here I've got two somewhat similar-ish features, but they are really dynamically distinct. So this one really is a tropical cyclone. So it's a tropical cyclone, it's governed really by convection, and it's much more circular. This is in contrast to something like a mid-latitude storm or a mid-latitude cyclone. This would be a cyclone, I guess. You can see that there's a familiar comma shape. So this would be manifesting from baroclinic instability. So that you have some sort of flow and it's tearing off an eddy, whereas this one really is you have a convection and that's driving some sort of circular flow. In the ocean, what sometimes you can observe is you can do this from things like chlorophyll. So this would be in, so chlorophyll, so I say chlorophyll, this is really how green something is. So that's used as a proxy for chlorophyll in the ocean. So these kind of mesoscale eddies could be shred off from the coast, so it can drag some material with it and do some non-local transport. So these could have anomalous but long-range non-local transport. This one is a different observation, and you might be able to see little small-scale features on top of this mesoscale eddy. So these would be the sub-mesoscale type instabilities, and that's important for things like biogeochemistry, as we heard about yesterday. So the main point is the mesoscales are really the bridging scale between the large-scale forcing in the atmosphere and the ocean, and also the smaller scales that we heard quite a bit about yesterday, which is to do with sub-mesoscales, to do with the waves. So normally what you have is you don't have transfer of energy from large scale directly to the small scales. It tends to proceed in some sort of for various dynamical processes. You don't tend to have a non-local transfer in the spectral space. So the mesoscale is the important conduit linking the large scales to the smaller scales. And it's generally known to be extremely energetic. So most of a lot of the energy is in the geostrophic variability. So I'm going to use the ocean as an example. So this is, so you might have seen some of this reference to the Ferrari and Wunsch 2010. So you got the large scale forcing, but then somehow it has to go to the small scales in some way. So the geostrophic variability is one of the pieces of Lego, which is linking, it's like a bridge, which is linking the large scale and the small scales. So the point here is that if you do not represent your mesoscales properly, one of the things you can screw up is the energy cycles, for example, within the ocean. So that's where the parametrization comes in. So we want to understand, when we do bioclinic instability or understand the bioclinic features, we want to understand how does that lead to fluxes of energy? How do you represent these? Is linear instability theory one possible way to help you represent these kind of processes in the case where you don't resolve them? And it helps us inform kind of parametrizations, for example. So that's why the instability part can potentially be important. Okay. So I think I'm just going to step back a little bit. I'm going to, so just so we're all on the same page. So here we're really talking about rotation. So yesterday there were some mentions of balance and etc. So I'm going to probably define what I mean by balance at least. So in rotating stratified fluid dynamics, one of the key parameters is the Rossby number. So the Rossby number is a measure of is a ratio between the effective and the rotation timescale. So when you talk about rotationally dominant, you have to measure it relative to something. So in this case, it's really the dynamical advection timescale. So in the atmosphere, one example you can do is you can do a quick calculation. So for a rough speed of 10 meters per second, so that's fairly small. Over about 1,000 kilometers, so a mid-latitude of a standard jet would have something like a Coriolis parameter of, would have a Rossby number about 0.1, so it's small. So the fact that this is small means this rotation aspect is big relative to the advection. In the ocean, what you tend to have is the length scales are smaller, but the flow is also smaller. So the Rossby number is not really tiny, but it's small, so it's still rotationally dominant. One interesting thing, so I used to work on MHD as well. So in the Earth's core, so if you believe that there is in fact a rotating stratified outer layer, so that would definitely, so the Rossby number associated would be absolutely tiny because the velocities are really small. So there is actually some talk about using the quasi-geostrophic theory, but the solid Earth's core. Okay, so if the rotation is tiny, if the Rossby number is tiny, then this tells you rotation is important. So to leading order approximation, the dominant force balance is between the Coriolis effect and the negative pressure gradient. So that's what I'm going to talk, that's what I would mean by balance. So it's a flow which is in this kind of force balance. So this is what's known as geostrophic balance. So the thing to notice is that there's a negative pressure gradient, a horizontal negative pressure gradient here. For large enough length scales where your Rossby number is small, you can usually make the approximation for hydrostatic balance. So for hydrostatic balance, you need the aspect ratio to be small. So if your horizontal length scale is much larger than your vertical length scale, then you're good. So here what you have is you've got your vertical pressure gradient, which is balanced by your weight of your fluid. So the thing you would notice is that in the previous case, there's a horizontal pressure gradient. In here, you have a vertical pressure gradient. You can cross-eliminate and get rid of the pressure. And the thing you would get out is what's known as the thermal wind shear relation. So this is now telling you that there is a relation between the horizontal gradients in density, potential density, buoyancy, isotropes, whatever dynamical thermodynamic variable you think is relevant. And that's related to the vertical shear in the geostrophic flow. So balanced states, or at least in the low Rossby number regime, there's a peculiarity or kind of useful quantity, observation is that the two things are not really separate. So you can't really talk about one, well, you can talk about one or the other, but they are intimately linked. So in some ways, it might actually be easier to talk about a combination of them or just one of them and imply the other. So Carsten talked about this yesterday. So by thermal wind, so he talked about when you have baroclinic instability, what you have is you have a vertical shear in the flow. And what that tells you, you have to have horizontal gradients in your density or your dynamical variable, your thermodynamic variable of relevance. So baroclinic instability would be the case where you relax the background vertical shear, but at the same time you have to flatten your isopycnals or flatten your isotropes or whatever you think is of relevance. Okay. So one pictorial example would be, let me just illustrate how, I'll give you a quick illustration of the thermal wind balance, a thermal wind shear relation. So I'm going to take the atmospheric jet stream as an example. Observation here, I'm in the northern hemisphere. Y increasing is going towards the pole. If you go up in altitude, you cool. If you go towards the pole, you cool. And from that, you can, if you take some data, you can imply that the isotherm has to bend down towards the pole. In the atmosphere, the dominant, the isopycnal, so the density is inversely proportional to your temperature. So your isopycnal has to bend up. The isotropes are kind of similar in some ways. So this one tells you that your d rho dy is positive. We're in the northern hemisphere, 1 over f is positive. That's just a constant, so that's positive. So this thing has to be positive. So it tells you that your UG has to increase as you go up in altitude. So this is one kind of explanation of the, at least one realization of why there should be atmospheric jet stream. And it's called thermal wind because it's actually, it comes from the atmospheric literature. So in the atmosphere, the dominant contribution to density is temperature. So that's why it's thermal wind. All right. So baroclinic instability is then the process of, something dynamical which ends up relaxing the flow. So the thing I guess I want to say here is that, so normally this is thought of as fueled by what's known as available potential energy. So when you talk about instability, you're really thinking of there's some sort of free energy and the instability wants to tap into that free energy. In this case, you might think you have a shear in the flow, so there is some background kinetic energy. But in the balance regime, what you have is you really also have the potential part, which is from the sloping isopycnals. And it turns out the potential part dominates over the kinetic part anyway. So normally we think of baroclinic instability as coming from potential energy. So the instability ends up wanting to relax the flow or slump the isopycnals. They're really one and the same in the balance, or at least in the rotation dominant regime. So the dominant source of energy would be a potential energy. So this is in contrast to things like barotropic instability, where you have a background flow and it really is coming from the kinetic energy view. So another thing which, so this is important for things like energy cycles, but it's also important for momentum transport. So one thing so this is a schematic I took from David Marshall. So this is what's known as form stress. So what you have is in the ocean, you might have a wind which is driving a flow in the top layer. If you have a fluctuating isopycnal here, for example, then you can imagine this sets up a pressure gradient in such a way. So the way you think about it is that you've got a tilting isopycnal. Your flow is pressing onto the isopycnal. On the way in the flow side is pressing, but on the lee side is taking stuff away. So there's a positive pressure and a negative pressure. So it sets up a pressure pattern, and in this case, what you notice is that it's such that the pressure always acts against what you would expect to be the momentum input. direction here. So it's going to the left, but it's always going to the right in the bottom. So the way you really think about it is that this is a vertical transfer of horizontal momentum. Okay, so form stress enables momentum transfer input by the wind in the ocean to take it down to the bottom. Okay, yes. So it's a vertical transfer of the horizontal momentum. But this would be, so if you put in momentum here, this is, I suppose this would be, well, so I guess one way to think about it is that this is decelerating the flow and this is accelerating the flow. So there's I guess what you not think of this as if this is a uniform layer, then everything has to be done throughout the layer. Yeah. Okay. But yeah, okay. So technicality aside, there is a so this is related to vertical transfer momentum. But again, so momentum is to do the flow, but in the balance regime, this is also related to things like the buoyancy or the something in this case to do the buoyancy. So the eddy form stress is somewhat related to eddy buoyancy flux, and this would be related. So the momentum transfer, it comes hand in hand with the buoyancy fluxes. So vertical momentum transfer and horizontal buoyancy transfers in the balance regime are one and the same thing, so they're intimately linked. Okay. So baroclinic instability you can think of as momentum transfer or really as a lateral buoyancy flux. So either you're slumping the isopycnos, or pulling momentum down. So it's a conduit for taking momentum down, for it to be transferred to the solid earth by topographic form stress or similar. Okay. So that's kind of the physical outline. So let's talk a little bit about equations. So normally what you do is you start with some equations. In this case, what you do is you propose an asymptotic expansion in the solution in the appropriate variables. So just to say, given the conversation I had yesterday, it's an asymptotic expansion. It doesn't necessarily mean this converges. It's just a proposed expansion. There's no guarantee of mathematical convergence or whatever. But it is a useful expansion to take. You get what's known as the quasi-geostrophic equations or the QG equations. So big D dt here is your material derivative, and it's the flow of relevance is your geostrophic flow. So in this particular case, at this order, the geostrophic flow is purely horizontal or along the geopotential, in the direction along the geopotential surface. It can be shown that this has no divergence. So you can introduce a stream function psi, and in this case, your variable q and your b can be written in terms of the stream function alone. There should be f0 here to be consistent. Q here is known as the potential vorticity, or the PV, so I'll be using this quantity quite a lot. Buoyancy here, in this case, would be the QG buoyancy. Here I would assume is beta plane, so instead of looking over the sphere, I'm just taking a tangent plane, and I'm going to take the Coriolis effect to be represented by this beta. So there's a latitudinal variation of your horizontal Coriolis effect. I'm going to represent that as beta. So PV has a contribution from the planetary part, from the relative vorticity part. So this is really the relative vorticity. And there's a buoyancy part. There's a vertical stretching term. So notice here the PV has both a thermodynamic contribution and a flow contribution. So somehow they're lumped in one. There's one master variable going on. The buoyancy is just defined by this way. All right. So the way I'm at least thinking about the QG is that this is really a statement of material advection of PV up to sources and sinks of PV. So in the interior, what you have is you've got advection of the potential vorticity by the geostrophic flow. At the vertical boundaries, it's really a surface buoyancy, but if you think of it in terms of what's known as like a delta sheet of PV, then this really is a statement. It's really something to talk about PV advection as well. So I'm going to stick to order Rossby. I'm not going to talk about going to higher order. So Manita is going to talk about some of that. You can ask Carsten about it as well. So I'm just going to stick with QG because it's much easier to talk about. All right. So I'm going to take a digression. I'm going to start talking about the CRW mechanism. I'm just wary of time as well. So I'm going to illustrate this with the horizontal flow. Let's just make the assumption this is horizontal flow. There's no beta. And what I'm going to essentially argue is that, so I'm going to illustrate a mechanism for shear instability, in this case for horizontal shear instability. So the first thing I want to work out is that, so it's motivated by the Rossby waves. So the Rossby waves are propagating on a background planetary vorticity gradient. So here what I'm really thinking is that if I have a shear flow like this, what's the associated background vorticity gradient? And what are the kind of waves or wave-like motions you can have on this kind of, within this kind of system? All right. So for this one, for this particular case, my background vorticity gradient is to do with my negative gradient of my background state. In the uniform, or at least the almost flat cases, there is no vorticity gradient. There's no there's zero vorticity. In this region, your flow is increasing, so it's a negative vorticity. So what I would have is, you can imagine this is the place where it's uniform negative vorticity. So there is a jump into the, or at least there's a transition from the 0 to the negative and negative to the 0. So this is a negative jump. This is a positive jump, or at least positive gradient in the background vorticity gradient, in the background vorticity. So what I'm going to make the assumption here is that within this system, my vorticity is the thing which is conserved. So I'm going to draw, the thought experiment you have is you imagine there's a material line on this white part. So let's, for argument's sake, if this was 0, -1, and 0, let's say for argument's sake, this is going to be -1/2. So I'm going to take this material line, I'm going to move it up and down into the other regions, or north and south in this region. And I'm going to make the assumption within this line that I move, there is no mixing of vorticity, so it preserves the vorticity as I move this kinematically. So I draw my waveform, I move my line of vorticity into other regions. So the argument would be that you take something which is -1/2 into a region of 0. So this is a negative anomaly because the -1/2 is less than 0. If I take a -1/2 into a region of -1, then this is a positive anomaly because -1/2 is bigger than -1. So I draw on my vorticity anomaly, so I'm going to call it Q because I got a bit lazy. So associated with the displacement, there is a vorticity anomaly. I drew 3 of these on, but it really is everything along the line. So I just happen to draw 3 for cleanliness. The next part would be, the next jump in logic would be that you have a vorticity. So your relative, if this is relative vorticity, this is related to the curl of the velocity. So the thing the logic here would be that you have a local vorticity anomaly, but that has a non-local flow associated with it. So in the electromagnetism analogy is you have a charge, but there is a non-local electric field. All right. So if you're going to make the assumption that this is some sort of waveform, then what you ask is that, well, okay, so this has an induced velocity. So what does the self-induced velocity do to the material line itself? You can argue that, at least at the nodes, so this one is turning this way and this one's turning the other way, is pushing it down, and here's pushing it up. And you can do this every other place, and you can argue that this is going to shift it in some way. You want to maintain a waveform, so you can either argue this by continuity or just by taking representative examples of -q at different magnitudes. So the thing I hope you would at least, you don't need to buy it, but I hope at least you will accept is that one argument would be that if you believe this kind of argument, then the waveform is going to propagate to the left in this kind of setting. And within this appropriate Doppler shifted frame where this point is 0, the wave is going to go to the left and is going to go against the mean flow. So that's where the counterpropagation comes in. So before I go on, are there any questions or anything anyone want me to clarify? Because everything later builds on this, essentially. For this one, because I'm going to take it to be in the horizontal case, so there is only, so I'm only going to consider relative vorticity, 2D incompressible. The analogy is that this would work for potential vorticity as well later on. Okay, so for time reasons, I'm going to move on. We can talk about it a little bit more. So you can do it at one, you can do it at another location. Suppose you do it at the bottom. So then the similar argument will give you the fact that this wave is going to the right. So the correlation between displacement and the vorticity normally gets swapped because the PV jump, the vorticity gradient jump is different, is a different sign. But again, still the main thing is that your wave is going to propagate against the mean flow. So the background state goes to the left, but your wave is going to go to the right. So you have counter propagation. All right, so the CRW stuff really dates back to Hoskins, McIntyre, Robertson. So they did this for the atmospheric case, and they thought about this in terms of the potential vorticity. It actually dates also back to Breverton in '66. So he looks at the two-layer QG system. So the key part is the counter propagation. There's the wave, and there's the Rossby part. So the Rossby part comes from the analogy with planetary Rossby waves. So in planetary Rossby waves, it's beta that gives you the propagation mechanism. When you have a background flow or background basic state, it's the background basic state that gives you the vorticity gradient, allowing these kind of waves to propagate. So that's why these are sometimes called Rossby waves. I would call them vorticity waves. Okay. And the key part is that these vorticity waves tend to counter-propagate against the mean flow. So previously I talked about where you have a case of one. So you can ask, well, what happens if you have two or more? Then you can start having interactions, right? Because the top wave can interact with the bottom wave and the bottom wave can interact with the top wave. So in a particular case where I phase shift them by pi by 4, so this is a quarter wavelength phase shift. So I shift the top in the potential vorticity anomaly from the vorticity anomaly point of view, I shift it back, I shift the top back to relative to the bottom, so it's tilting into the shear from this point of view. What you can see is that the green is pointing up and down exactly where there's a peak and a trough on the top wave. The top wave is such that it's pointing down and up exactly where there is a trough and a peak. If in addition you can maintain, so there is no guarantee that these things won't go out of phase, right? But somehow if you can make the assumption that this stays within the same phase configuration, then you have a continual constructive interference here. And this would be one explanation for exponential or at least modal instability. So there's a counter propagation, there's a phase locking in, there's a mutual amplification. So there's a continual amplification of the wave displacement, at least from this point of view. You can possibly convince yourself if I shift this by if I shift the bottom wave from the unstable case by half a wavelength, then these are going to be mutually destructive. So this would be a case where you have the stable mode. So the first one would be the unstable mode, and this is the stable mode. So a little bit more technical details. The interaction of the domain of influence is given to you by what's called a Green's function. So the wave, there's a limited extent of how the waves extend in distance. And that's dictated by the physics, so that's given to you by the Green's function. So there's an interaction which is given, affects the amplitude and the propagation. If you can get phase locking, so in the appropriate Doppler shift, the phase locking could come from, it would need to come from both the mean flow and also the mutual interaction. So the two waves could be hindering each other and driving it to some sort of equilibrium state. And if you happen to get phase locked within a constructive interfering configuration, then you have modal instability. All right. Yeah. That's correct. So you have two. So this, I guess, this really is a kinematic argument. Is how. Well, I don't know about nonlinear, because all of this is really in the linear phase, right? There is
not one wave, but the other wave is affecting the one wave by nonlinear terms. The one wave is affecting, or is the mean flow for the other wave, and then you can linearize, but it's still a nonlinear term.
I suppose.
Yeah, I think that's right. Each wave's advecting the other one, right?
Yeah.
Okay.
So that is something I will probably talk. So here I just sketched it out. So there's the mathematics of it, which is in the second part. I'm not going to talk about it in the first part. So there is that aspect of it. So one reason I can't talk about this here is that, so the analogy is that this would work when you talk about potential vorticity anomalies. There is going to be some extra issues with the stretching term, with the buoyancy term. But in principle, you can imagine that ultimately the key bits is I need two waves which carry vorticity anomalies. So what's stopping me? There's nothing stopping me from doing this for things like gravity waves. So gravity wave, when it propagates, you normally talk about the displacement, but there is associated with some sort of, if it has a flow, then it has a vorticity associated with it. It could work, for example, for cases like in the MHD regime. So in the MHD regime, what you have is you've got different charges. Then you have something which gives you the twist, which would be the Lorentz force. So what I'm trying to argue is that the CR, at least this kind of mechanism, relies on the fact that you have some waves which are interacting through some sort of non-local action at a distance. The details depend on how they interact. So how these things propagate and how they interact would come up from the Green's function. So the interaction comes from the Green's function. But at the very coarsest point of view, you just need two waves which are constructively interfering. All right, so I have some papers which do this for the MHD case. All right, and there's some relation to the PD symmetry here. I'm just wary of the time, so I'm going to fly through this a little bit. The instability analysis, okay, so this is the picture for the shear instability. So one thing you want to ask is that if you do baroclinic instability analysis, do you in fact see these kind of things? So it's one thing kind of speculating about it. Like, do we actually see it when we do the instability analysis? So the prediction with CRW, if you buy this picture, then you expect, in this case, the PV structure in a baroclinic instability problem to tilt into the shear. So this we actually know. There is an optimum phase shift of pi by 2. So just now the picture I showed is that there is a max, you would expect that's the maximally constructively interfering setting. I'll come back to this in part 2. So that's it in terms of is actually not true. It's true in the instantaneous case, it's not true in the sustained case. So for those of you who've not seen a linear stability, and I assume you've seen it, I'm just going to recap it. So you take a basic state, you take a flow in this case, for generality, I'm going to take this flow. It's in X, but it's only in X, but it only varies in Y and Z. By thermal wind balance, that my buoyancy profile is fixed by this profile, so I don't have to choose my buoyancy profile as such. Linearize, so be wise and linearize. It rhymes, it must be true, so you should probably do it. So I'm going to linearize against the basic state. So now your PDE or your ODE is going to be linear, so you know how to solve these things. I'm going to assume solutions of some form. In this case, I'm going to make the assumption that there is periodic wave-like solutions in the X direction, but the eigenfunctions could be in Y and Z. C here is going to be complex, so here what I'm really thinking is that I am in some frame where my instability, I'm following the instability in some sense. So my C is complex. You don't have to do that. You can take K to be complex, then you have a spatially developing instability. This is kind of more standard to do. Then the name of the game is you want to say something about a C. So you want to compute the dispersion relation given some wave number and your background flow and some parameters. If your imaginary pi is positive, then your eigenfunction is going to grow like exponentially to the KCI. So that is a modal instability. Not going to talk about algebraic instability or transient growth here, just going to talk about normal mode type instability. If you take the linearized QG equations, then you linearize, so everything's linear now in the perturbation variable, right? So this is order 1, this is a leading order, this is order 1, there's no non-linear terms. Normally there would be dB dy here, I just swapped that over the UDZ by thermal wind. If you take modal solutions, you get this form. So here I haven't said anything about U for the moment, so I'm going to keep it general. One way to do this is you do some general analysis, and it turns out that you can derive what's known as the stability conditions or necessary conditions for instability. This is a bit like, if you know about the Rayleigh problem, then this is the Rayleigh inflection. It's a bit like the Rayleigh inflection point theorem. The analogous of case for the baroclinic instability is what's known as the CSP or the Chernystone-Pedlowski condition. A necessary but not sufficient condition if any of these are satisfied, any one of these are satisfied. So the logic I just like to highlight is that you need at least one of these to have instability. But just because you have one of these does not mean you have instability. If you have none of these, you definitely don't have instability. So just be a little bit careful about this. This is necessary, but it's not sufficient. All right. There are finite amplitude analogs. You can either be clever and construct wave action at the linear level, or you can start from the Hamiltonian formulation and then work out the wave actions by symmetry. So you can use Noether's theorem for these kind of things if you like. So if you're interested in this stuff, look into the paper by Ted Shepard in the 90s. So one physical interpretation of relevance here is that so there is a suggestion that these kind of conditions are really conditions to have CRWs. So Yao, so my postdoc supervisor Yao was arguing that the Rayleigh's theorem really is the inflection point theorem tells you that you have a change in the sign potential in the vorticity gradient. If you do not have that, then you cannot get counterpropagation. Then there is no way in hell you're going to get a shear instability. If you believe the CRW is the Lego of the, it's the building blocks for shear instability. So one way to think about this is that the first one is really something about your CRWs being in the interior of the domain. The second one is you have a vertical boundary, so these are kind of thermal Rossby waves, and something in the interior, so either this one, or this one, this one. The third one is the Eady case where you have bottom and the top. So this would, this is somewhat consistent with the fact that these are necessary but not sufficient. You need counterpropagation, but just because you have counterpropagation does not give you instability necessarily. You need phase locking as well. And because of this kind of thing, if you believe in this kind of thing, then you would immediately imply the Eady modes are going to be deep, because the perturbation is all through the whole domain. Whereas the Charney-Green problem would have more vertical limited disturbance, which is actually known for the Charney-Green problem. All right, so for the Eady problem, it's going to just introduce the Eady problem. So you take an F-plane, there's no beta. You take a linear shear flow. In this case, so normally this is lambda z, so I happen to take lambda z over h. So lambda over h is my shear. If you work this out, there's no PV in the interior. So all the PV stuff is on this delta sheet. Okay. So it's the top and the bottom. So it's a third of the condition. I'm going to make the assumption this is rigid lid and flat top and bottom. So there's no slope bottom for the moment. So what I'm going to have is I'm going to have some sort of thermal Rossby edge waves living on the top and the bottom. And these are going to interact. If you do the Eady problem, you do all the maths. So you shove this in, you non-dimensionalize. There's an F, which is like the inverse Berger number. So this is just maths. I'm not going to go through it. So your interior stuff and then your boundary condition. The modal solutions here, because my thing is only a function of z, so I can take an L wave number. So modal solutions look like this. If I make the assumption this is not zero, so this is a fairly heavy assumption, but let's make the assumption this is not zero. This is a second order ODE with second order ODE. Solutions are signage and Koch with a rescaled wave number. But the thing I don't know is A and B. So somehow your A and B needs to be fixed by your boundary condition. So your boundary condition is these two. So if you take the side tilde and shove it into the boundary conditions, then you end up with a 2x2 system. So this is one peculiarity of the Eady problem. So normally you have a PD or ODE to solve. In this case, you reduce it down to algebraic equation, a 2x2 algebraic, a two-dimensional problem. So this has non-trivial solution if the determinant is zero. So you can work out when it's zero. For this particular case, it's this guy. So I took it to be, I symmetrized the flow. Okay. You can solve this analytically or numerically, and once you have your eigenvalue, you can get your eigenfunctions by working out A and B. So you shove it back. So I'm just going to show you an example. So the L equals 0, I'm going to take L equals 0 because normally the 2D modes are the most unstable. Yeah. Yeah. I know it's 5 minutes, I guess. Yeah. Yeah. Okay. So the key features I'd like to highlight here is that the C, so here there are two modes. So this is a C squared. So so here I'm showing the growth rate and this is the phase speed of the two modes. So the two modes have the same phase speed when it's exactly when it's unstable, and they are absolutely not the same when they're not unstable. There's a maximum growth rate. There's an implied K, and from the K you can imply a length scale because the wave number goes like one of the length scale. So the most unstable mode has a preferred length scale, which is about 4 times the Rossby deformation radius if you redimensionalize this. These are deep modes, so the eigenfunction looks like these. These are deep modes. The stream function tilts into the shear. There's a diagnosed phase tilt, in this case of pi by 2, which is consistent with the CRW mechanism I talked about before. What other stuff is there? I think that's basically everything you would care about in the standard Eady model. Right. There's a digression, but I think for time reasons, I'm going to just quickly go through this, and if there are, just leave some stuff for discussion. So it will take me two minutes or so. Okay. So from a more theoretical point, so one of the things I've always been very interested in is the implication of symmetry. Implication of symmetry on the solution problems. So in this case, what you observe is that the Eady problem is in fact what's known as parity time symmetric. So parity is flipping in space, so you mirror in the space, and time is when you mirror in time. So the problem itself is not symmetric with just flips in time and time or space by itself, but it's, if you do time and space together, the equations become invariant. What that means is that the solution has to have certain properties. So PD symmetry is a concept that comes from quantum mechanics and quantum field theory. So there they talk about things like charge parity time symmetry violation, and that gives you extra particles, etc., extra forces. So the definition of PT symmetry is that it's to do with a non-Hermitian operator. So these are non-Hermitian operators that have a certain symmetry, and sometimes they can imply a real spectrum. For the particular case here, it's fairly trivial. The standard Eady problem is that your operator looks like this and is clearly symmetric under the PD operator. You can have a look at this paper itself. That turns out to imply why there has to be this CR. There has to be a coalescence of the mode. So mathematically, and because of the symmetry breakings, you have to have this. So this is just some food for thought. We can talk about it a little bit more. I'm going to skip the parameterization. So there's some idea using linear instability to tell you features about parameterization. The main thing is this kappa. So there's a diffusivity, you don't like this guy. You propose a closure, but you want to say something about this kappa GM or some diffusivity or eddy transfer coefficient. So there's one idea that your instability would tell you some information about that. But for time reasons, I'm not going to talk about it. Feel free to ask me about it. So I'm just going to stop here for leave some kind of material for discussion, and then in the second part, I'll talk about some stuff which is actually new. Okay, thank you.
Okay, we have time for a couple of questions before break, so sure.
Oops, sorry.
Yeah, can you hear me? Yeah, just a couple of questions. One thing I didn't understand is, I get why phase locking is important so that you can have a constant constructive interference. I don't understand why they have to be counter-propagating for that to be the case. If they were to be propagating in the same direction and to be phase locked, why you wouldn't have that constructive interference?
I think the thought experiment is that you can't get phase locking if you're not counter-propagating, because you don't have enough. There's nothing holding the thing. You need multiple things to hold the waves in place, and the counter-propagation is one crucial ingredient. But just because you have that, that's not enough. You need a little bit.
Okay.
Is it a definition of what you mean by counterpropagation? I mean, you could add a uniform U to the whole thing.
And it makes no difference, I guess. Yeah.
Right.
Yeah.
And
yeah, counterpropagation in a sensible frame of reference.
the other thing I didn't quite understand is you begin by talking about how baroclinic instability feeds off of APE, but then when you go through the counterpropagating Rossby wave and when you do the last few slides that you covered, there's no discussion of APE at all. It's pure kinematics.
That's right, because in this case it's purely linear, so there is no feedback onto the mean state. So that's just the assumption I make. I make no assumption about feedbacks. I'm just talking about how, if in the linear phase where you make the assumption that the background state is essentially static, what kind of perturbations would grow. But I do not talk about the case where the perturbation grows sufficiently where it feeds back onto the background state. That's no longer in the realm of linear stability.
So the growing instability doesn't have an attendant increase in KE?
Sorry, say again?
The growing instability in the linear theory doesn't have a corresponding increase in KE. It's only in the nonlinear theory where...
No, it will do.
So where's that coming from?
So so it comes from the fact that your background source is essentially held fixed, right? So you have an infinite pool that you are not allowed to deplete, at least at this linear theory order. So there is an infinite bath from which you can draw stuff on, because so if I, for example, run a time-dependent calculation, then it will just blow up exponentially. It would be arbitrarily large, but that would not be physical necessarily, right? Because here, again, it's like what we talked about yesterday. It would grow to the point where your assumptions are no longer valid, so the feedbacks become important. So here I'm explicitly saying that there is no feedback at this order. It can and it certainly will violate that assumption, but it's certainly accurate at the infinitesimal linear phase.
Okay, thanks.
And then the next bit, so related to this, just one point. And then sometimes you can talk about eddy kinetic energy here. I would argue that's not necessarily the right thing to look at, because that's not necessarily the thing which is conserved or sign definite. So this is covered. There's a very subtle difference when you talk about what do you mean by a wave amplitude. So wave energy is one possibility, but wave energy is not necessarily the best one. For these kind of problems, it turns out it's probably something like pseudo energy or pseudo momentum, which is slightly better to talk about. But that's a technical subtlety.
I'll just ask one quick question, then we'll go for coffee. At the end, you were saying the PT symmetry implies phase locking. Is that? Did I hear that right? Is that?
So the PT symmetry for this one happens to correlate exactly with phase locking. So there is no.
So we could have inferred the phase locking from the symmetry itself.
That's right. So one interest I have is that, so let's go back to the PT symmetry. So this is actually right at the end of my conclusion. So that's why I got interested in the PT symmetry aspect. So PT symmetry happens to be, so it turns out, so for technical language is that these are points, so in the stability regime, this is stability regime, this is the stable regime, and this is the transition, the boundary between the two. From a PT symmetry point of view, this would be the region that is known as so this is where the PT symmetry is preserved. This is known as an exceptional point. You have what's called crine collision at these exceptional points, and you have a coalescence of mode. And then within the instability region, you have, so this would be the places where you have spontaneous breaking of PT symmetry. So that refers to the eigenfunction. It so happens in the Eady model and in some of the other shear instability models that these are one-to-one correspondence, or there's certainly a one-to-one correlation between these kind of concepts. So one suggestion would be that in this case, you can solve this exactly, and then you can make the correlation. In the more general case, can you somehow do the reverse? So you analyze, you have a general shear operator, and you say, where are your exceptional points, or what's your condition for these exceptional points? And if you can predict those, can you somehow use that to infer for a condition for stability? So you flip it around in some way. So that's why I got interested, because I think there's a lot of work which has been done in the quantum field theory, looking at non-Hermitian operators and the reality of the spectrum. And possibly this could imply results for classical shear instability.
Okay, well, interesting. Thank you. I think some of us need coffee, so let's thank Julian again and go get some coffee. Thanks.